Hello and welcome to this lesson video where we will learn about the machine power that's required to overcome the typical resistances that a heavy construction equipment experiences during a haul trip. The video covers the shown three learning objectives. To select the appropriate equipment for a haul operation, the contractor needs to consider the shown factors. The soil type and properties can affect the payload of the equipment and even limit the type of equipment that can be used. The total haul quantity and payload or capacity of each equipment determine the number and type of equipment pieces needed in a job to finish within a desired duration. We will cover in this lesson and the next lesson the mechanical properties of earthwork handling equipment, which can have a great impact on the productivity and cost. We can illustrate this point by sharing this question that is common in earthwork projects. Why does a machine only travel at 10 miles per hour when its top speed is 30 miles per hour? This question is important as speed affects the individual cycle time of the equipment, which impacts the production rate achieved by the equipment, which lastly impacts the unit cost and total cost of the hauling operation. To answer this common speed question, we'll need to learn about the following three equipment power attributes: the required power, available power, and usable power. In this video, we'll focus on the required power. An earthwork equipment should have the power required to overcome the total resistance to its movement between the cut and fill areas on the site. So, in calculating the total resistance, it is the same as finding the required power value. Just to clarify, the terms power and force are used here to refer to the resisting forces. So don't tell your physics teacher we are mixing power with the force. To move forward, we'll consider the total resistance to be made of rolling resistance and grade resistance. From its name, rolling resistance is the resistance that is experienced to roll the equipment, wheel, or track. As you can see, rolling resistance sources include internal gear mechanism to deliver the power from the engine to the wheel, the flexing of the tire on the road surface, and the penetration of the tire in the soil. From its sources, you can conclude that the rolling resistance is majorly controlled by the whole road condition and the interaction between the equipment tires and the whole route surface. To reduce the rolling resistance on the hard surface roads like asphalt, it's better to use tires with narrow tread and high air pressure. On the other hand, soft roads like natural soil will be better matched with broad tread tires with low air pressure. We can see this pattern in natural history, where camels have been used for centuries to transport goods in deserts. Camels' feet are wide so they can walk on sand more easily. Their huge feet help them walk on the sand without sinking into it. Same applies to heavy equipment and loose natural soil. Using low pressure tires increases the tire flexing and distributed the load over wider tire soil interaction area. The broad tread helps in locking into the soil, especially when it is loose or very muddy. For track equipment, there are no wheels to worry about their interactions with the soil. So the overall condition and shape of the whole route surface is the determining factor. Although track equipment is not that impacted by it, they are slow anyway. Now, how can rolling resistance be estimated ahead of the project to be able to estimate the equipment speeds and production rates? There are three ways, which we will cover briefly. First, the rolling resistance of a whole surface can be experimentally estimated by using a towing dynamometer on a leveled road. The rolling resistance in this case equals to the tension in the cable attached to the dynamometer. The rolling resistance can be empirically estimated by using the shown table that was driven based on a previous research field experiments. But this formula still depends on estimating or measuring the tire penetration, TP. Finally, the rolling resistance can be estimated using the shown table, which considers the type of the whole surface and the type of the equipment and tire. The values are given as rolling resistance rate, like kilogram of rolling resistance force per each metric ton of equipment weight. Remember, the weight here is the gross weight of the equipment, meaning its own weight plus any load it carries. The rolling resistance values are also given in the US unit system. You can see that the rolling resistance for all equipment configurations increase with the decrease of the whole surface quality, from having a smooth, hard concrete to a very muddy, rutted soil. However, you can see that high pressure rubber tires achieve the lowest rolling resistance on smooth concrete. On the other hand, crawler equipment have the lowest rolling resistance in the muddy soil surface. If crawlers are not available, then equipment low pressure tires could be the second option. So we can conclude here that rolling resistance is very dependent on the quality of the whole surface, which is a factor that can be controlled ahead of starting the whole operation. Soils with low bearing capacity may require using crawler track-mounted equipment, not wheel equipment. However, the quality of the hauling roads can be improved in two ways. Contractors can use water trucks and graders to level and smooth the whole route. Water trucks are also helpful in controlling the dust from the hauling operations. Also, geotextile sheets can be applied on the whole routes to increase their bearing capacity to reduce the rolling resistance for heavy equipment with large payloads. Now we're done with the rolling resistance, let's cover the grade resistance. Grade resistance refers to the gravitational force in the equipment when moving on a sloped road. The equipment resists this gravitational force when moving uphill and benefits from it in accelerating when moving downhill. Let's now derive a general formula for the grade resistance force using some basic principles of statics and equilibrium. The grade resistance, GR, force, equals the component of F of the equipment weight parallel to the slope. Sloped surfaces are usually described by their grade percentile value, G percentage. A positive G percentage is used when the equipment travels upward or uphill on the slope. From the geometry of the shown free body diagram, F equals W times sine alpha, where alpha is the angle between the vertical equipment weight and the line perpendicular to the sloped surface. This angle is the same as the slope surface angle with the horizontal ground, which is tangent to which its tangent equals the vertical rise over the horizontal run, or the grade value G in decimals. Now we can assume that most hauling routes have small angle of slopes. At such small angle values, the tan and sine values of the angle are very close, so we can substitute the sine alpha in the F formula with tan alpha. And tan alpha is the same as G percentage over 100%. So we can end up with the grade resistance force to equal the weight W times G percentage divided by 100. Here's a small example of 50,000 Newton tractor going on a 2% grade. By applying the formula, we find that the grade resistance equals to 1,000 Newton. So far, we learned about the separate components of the total resistance or the required power. Now let's see how to add them together. As we'll see in the next lesson about performance charts, it's common to represent the required power in equivalent grade percentage value. This means that we can keep the whole hauling route slope in its given grade percentage, but we will need to transform the rolling resistance, expressed in kilogram per ton, to an equivalent grade resistance. It's like transforming a leveled rough surface with a rolling resistance R, kilogram per ton, into an equivalent smooth sloped surface with grade GRR. Let's illustrate this transformation using an example. We need to calculate the equivalent grade resistance of the rolling resistance that is expressed by 20-ton truck on a loose sand with rolling resistance rate 150 kilogram per ton. Like we did to drive the grade resistance formula, we will use the same approach to find the equivalent grade of the rolling resistance. In this lift small free body diagram, FRR is the total rolling resistance force for the truck. We need the truck when moving on the rough horizontal surface. We want to transform this case to an equivalent resistance case where the truck is moving upward on a grade with grade GRR percentage. FRR equals the weight, 150 ton, times the rolling resistance rate, 20 kilogram per ton. We set FRR equal to the horizontal component of the weight, which is shown in the right hand of the equation. So we solve this equation to find that having a rolling resistance rate of 20 kilogram per ton is equivalent to driving uphill a 15% grade. So we can generalize a formula for calculating the equivalent rolling resistance grade percentage using the shown formula. So we don't have to set up and solve this equilibrium problem for every equipment in every project. If we are dealing with the US units, a similar formula can be used for pound per ton rolling resistance values as shown. Now we can add the physical grade resistance and the rolling resistance equivalent grade as two percentile values to get the total resistance value. But when we add the grade and rolling resistance values, we need to pay attention to the sign depending on if the equipment is driving uphill or downhill the grade. The grade resistance will be positive driving uphill and becomes negative when driving downhill, which means it's not resistance anymore. So in this video, we covered the calculations for the required power to overcome the total resistance forces, the equipment force faces on a project site. We will cover in the next video how to counter this required power with the available power from the equipment and check how much of it is actually usable. That's it. Thanks for watching and take care.